Hello and welcome back. We are discussing section 4.2, logarithmic functions. Our task for this video is to define and explore logarithmic functions and their properties. So first we'll just do the usual deal and start off with a logarithm. So we need a definition to get started here. So logarithm with base b, we'll pick a positive number for that base, and it's not 1. That's basically just to get the exponent that it's paired up with to make sense. So this expression, log with a little subscript b of x, basically just means reorganize this exponential equation, this equivalent equation, so that the exponent y is down on the ground floor. So really we could call log something like inverse exponent, because that's really all a logarithmic function does, is it's an inverse function for the exponential function. So the way this is going to play out for us mostly is that logarithms help us get exponents out of that position and down onto the ground floor, often so that we can solve for that variable. Okay, so just to get some ideas of how these logarithms are working, we've got log base 4, or log to the base 4. That matches the base of the exponent. So basically, no pun intended, we want the base of the logarithm to match the base of the exponent so that they're inverses of one another. But basically, we're just taking this equation and reorganizing things. So log base 4 of 64 is 3, and that's because when we look at our exponential situation, we've got, get a different color, the logs are equal to whatever this exponent is actually. So just trying to identify key pieces here. The base of the log is the base of the exponent. What the log is equal to is actually that power. And then, almost by process of elimination, but by definition, this 64 is the result of this exponential expression. So if we take 4 to the third power, we get 64. That's what it means for log base 4 of 64 to be equal to 3. So this is just snagging that definition of logarithm. Slightly more complicated, but the same principle. We've got base of 5. And basically, the question that a logarithm asks is, if this is my base, what exponent do I need on 5 to get square root of 125? So in other words, the question this is trying to answer is 5 to the what equals the thing inside of the logarithm. So in this case, it's square root of 125. Well, square root of 125 is not an especially nice number, but all right, we can work with that. So we've got 125 is actually 5 to some power. 5 to the third would get you to 125, but that's not quite good enough. We need the square root of 125, so if we have 5 to the third to the 1/2 power to build in that square root thing, then we're in business. So 5 to the 3/2 power is the same as the square root of 125, and that's supposed to tell us that, in fact, this result of the logarithm is how we get this exponent. Okay, so we're not going to spend a whole lot of time doing stuff like that, but that just gives us some perspective on how logarithms actually play out here. So the rules that go along with this are actually pretty daunting when you first take a look at them. But the thing is here, so when we think about logarithmic rules, every single one of these is stolen from exponential functions. So logarithms exist entirely as a way to undo exponential functions. So they end up having their own interesting kind of characteristics and models that go along with them. But all those models are based off of the inverse of an exponential function. So everything that comes out of this, log base b of 1 is 0. Well, that's because b to the 0th power would have to be the number 1. Log base b of itself, log base b of b is 1 because b to the 1st power is equal to b. So it's still that same kind of question and answer setup that we had on the examples in the last slide. And then all of these things, so the equality rule comes from the fact that the exponential function is a one-to-one function, so its inverse is a one-to-one function. That means if the inputs are u and v, then the log of those things is going to be, well, so the other way around. The log of u being equal to the log of v implies that the inputs have to be equal to one another. The product rule, power rule, quotient rule are ones we typically see used in college algebra classes. Basically, multiplying something inside of a log is the same as adding the results of those two logarithms independently. And then the one that we use very frequently when we're working with solving equations is if you take the log of something to a power, then basically this exponent gets to come down as a multiple out in front. So we still have log base b of this number, whatever this number u is, but this exponent gets to come out as a multiple. That's really powerful because often we're using logarithms to get some variable out of the exponent position like this. So this is a delightful rule that lets us bring that down on the ground floor. Quotient rule works the same way. The log of some quotient is the same as the difference of those logs. So u on top, so that one is first, and then subtracted log of the bottom. Okay, so one more contrived kind of example. If we want to hold on to exact values, log base 2 of 3, that's as simple as it gets. We could get some decimal approximation to it, but we're not going to have some tidy number for it. Similarly, log base 2 of 5 is some weird number. So let's just call these variables to some constants to simplify things for us. So we'll call this first one u, and we'll call the second one v. And then our goal would be to take an expression like this one and rewrite it just using the u's and v's, basically. So I have no other logarithmic expressions involved. So, okay, so the first thing we could do is note that we've got a quotient here. The stuff inside of the logarithm is being divided. So that turns into two things getting subtracted, 15 first and then 2. So this is the quotient rule. Now, we have to be a little bit careful. You know of another quotient rule. You know of a quotient rule for derivatives. This is not that quotient rule, so maybe we should be careful. This is quotient rule for logarithms. There's lots of different quotient rules in math. And then we can keep going. We've got this looks like something familiar. This looks like the number 1, actually, because it's log base 2 of 2. So 2 to the what power gives me this number. So that's a question mark with an equal sign, written kind of small there. But so 2 to the first power would give us 2. So this expression really is just the number 1. And then in the interest of turning this 15 into something more like u's and v's, you might notice that 15 is the same as 3 times 5. There's no log property going on there. We're just rewriting the input, 15 as 3 times 5, which is absolutely its equivalent. But then we've got a situation where the product rule for derivatives could pan out. We've got two things getting multiplied inside of a logarithm. That's the same as having those two things getting added separately. So the log of the first quantity plus the log of the other. And then finally we have things that look like u and v respectively. Log base 2 of 3 is what we were calling u. Log base 2 of 5 is what we were calling v. So this is sometimes referred to as expanding this logarithm, sort of breaking it out into these component pieces like the two we were given. So graphs of these functions are the same as the typical graph between any inverse functions. If we reflect them over the line y equals x, then we get the graph of the other one. So we probably imagine starting with this, for instance, 2 to the x graph, could have had any base, but here's a very awful idea of what the y equals x line looks like. But if we imagine this is a mirror, and we flip one of these functions over that mirror, either direction, but let's start with the exponential one, then what we get is the graph of its inverse. That's true for any inverse functions, but in particular for the inverse functions 2 to the x and log base 2 of x. And then this is, instead of tools to work with logarithmic expressions, this is more like what are the properties of a logarithmic function in general. So I'll go back to the previous slide here for a moment because a lot of these things can be illustrated from the graph. The domain of this function is only x greater than 0. We can't actually plug in 0. And there's a very interesting characteristic right at 0. And that characteristic is a vertical asymptote, which is convenient. The x-intercept is at 1, 0. There's no y-intercept. Remember, no y-intercept because the function isn't defined at x equals 0. And then basically the rest of the limit statements say that if the base is bigger than 1, then as we get close to 0, the graph is just going to plummet. It's going to drop toward negative infinity. And as x gets bigger, we're going to get larger, although this does it in a very slow fashion. So although it is a monotonically increasing function, it's not very fast. Even any lines will eventually overcome this function. And then if b is between 0 and 1, it's sort of a similar kind of scenario as with the exponential functions, then basically this whole thing gets flipped around. Now as we approach 0, instead of going plummeting toward negative infinity, it's rising toward positive. And as x gets really big, this is actually dropping off. So just to revisit the pictures here for a moment, so here's a graph of atypical logarithm. They don't change all that much when we change the base. So it does pass through 1, 0. There's our x-intercept. It has no y-intercept because it just sort of drops off here. And then it does rise to the right, but not in a very rapid fashion. So those are some of the basic characteristics of the logarithmic function. One particular logarithm that we're especially fond of, the natural logarithm, is written in most undergraduate textbooks as natural log of x. Mathematicians tend to write this as log of x, which a lot of you, if you've seen logarithms before, think of as log base 10 of x. So we'll try to avoid confusion. We'll just use ln to refer to natural log since that's the more common at this level. But basically, it's the particular log such that we use this fancy number e as its base. And it gets used so often that instead of writing log base e, we can just write ln. So this is not NL, although that seems like it would be a common abbreviation, but it turns out not all mathematics was developed by English speakers. So this is probably something more like log natural, but there it is. So this is the particular flavor of logarithm who is the inverse of this exponential function with base e. So it has a similar, the usual kind of reorganization. The log is equal to y, which is the exponent in this equivalent equation. And then it's got base e, so the exponential function that goes along with also has base e. The most useful applications of logarithms that I can think of are in solving equations. So this is actually a logarithmic equation that we're going to undo, but we'll also visit the other scenario where we have exponential functions that we undo using logarithms. But this inverse nature is basically what we're going for. So there's two different ways we can think about evaluating or proceeding with this. I guess the first thing to note is x is tucked inside of the argument of this logarithm. I can't divide by ln or something like that. Ln is not being multiplied to these things. Ln is the name of a function, and just like we think of f of x, for instance, I'm supposed to think of ln of stuff as the inside of this function. There's no way to divide by f and just make this go away. This is mathematicians' fault. It's our fault for using parentheses to mean multiple things, but we'll try to figure out from context what's going on. So natural log is wrapped around this 2x plus 1, so really the only thing we can do is try to get rid of natural log. So one way of thinking about it is we're using the definition of the natural logarithm that we had a moment ago and rewriting this equation, which would end up looking like, let's see, logs are equal to the exponent, so the new exponent would be -2. The base of the natural log is e, and then we basically pop out the inside of this expression. So that's just using the definition of the logarithm basically to get us there. So there it is in more nice typographical fashion. The other thing you can think about is basically applying exponentiation to both sides. Basically say e to the left side is e to the right side. That's an equivalent way of going about this because e to the natural log of something are just going to cancel each other out. We're going to end up with just this input. So whichever way you think of it conceptually, this is the next step in our equation. But once we do that, we're down to good old familiar algebraic strategies. We can take away 1 from both sides. Take away 1 from both sides. And divide everybody by 2. So if we have e to the -2, take away 1, and then divide by 2. This is as precise an answer as we can get if we want to be exact. Out to 3 decimal places, it looks like something around -4.32. 0.432, that is. We'll be back in the next video to talk about solving exponential equations using logarithms. Talk to you then.